Okay, so in this lecture we're going to discuss clustering in general and one specific algorithm for it called k-means. So the clustering problem is fairly simple. We're given data x1 through xn, and we want to partition it into clusters, as I mentioned previously. The goal is going to be to find these clusters only given the data and some modeling assumption. And we want to learn clusters such that observations or data points that are in the same cluster are considered similar. So for example, they're all close to each other. And data in different clusters or in different groups are considered different. They're somehow far apart. So for example, here's an image on the right. Now the color coding corresponds to cluster assignment, so these are not labels anymore. We just have these two-dimensional vectors. That's all that we have in our data set. And you could look at this and say that the data naturally falls into two clusters. All of the data in this region is one cluster, and all of the data in this region is another cluster. How can we define an algorithm that's going to tell us that? That's going to learn what these clusters are and tell us for each individual data point what cluster it belongs to. So to do this, we're going to use a latent variable that I'm going to introduce right here before we move on to the k-means algorithm. So we're going to introduce this latent variable c. And if we assume that there are k clusters underlying our data set, and this is going to be just a parameter that we set. We say that we set k to be some number, and I'll discuss later some ways of deciding this number. Then for the ith data point xi, if xi is assigned to the cluster k, the kth cluster, then ci is going to be equal to k. So this auxiliary variable ci is going to be an index of what cluster the observation xi belongs to. So in this sense, we can almost think of this as like a supervised problem, except where we don't have the labels. Now we have clusters. Each cluster has a label. This is the label of which cluster the ith data point belongs to. But we don't know in advance what these labels are, so we want to simultaneously learn the clusters and learn the labels. So let's discuss the k-means algorithm. This is the fundamental clustering algorithm. It's also, I think, the simplest and, in many cases, the most useful. It's the most, I think, probably the most widely used. So in this problem, we again have data x1 through xn. And for now, let's assume that each point is a vector in Rd, just to make it simple. And the output of our algorithm is going to be a vector c, also of length n, and a set of vectors mu, k vectors, k-mean vectors. So this vector c is exactly from the previous slide, where the ith entry in this vector is going to indicate which cluster the ith data point belongs to. So if ci and cj are both equal to k, then that says that the point xi and xj are clustered together in cluster k. And then mu is going to be a set of capital K d-dimensional vectors. Each mu k is in Rd. This is the same exact space as x, so these vectors live in the same space as the data. And each of these mu k's are going to be called centroids, and they're going to define the center of a cluster. So mu k will define the center of the kth cluster, and then the data assigned to mu k are somehow going to be near that point, that centroid. So our goal now is to learn these two sets, the vector c and the set of centroids mu. And so in order to do this, we need to define an objective function. We need to have a mathematical way of telling us what values for c and mu are better than what other values, and a way for optimizing and finding a local optimal, locally optimal setting for c and mu. And we're going to pick one that's going to be easy to optimize, as we're going to see with k-means. Okay, so let's get right into it and look at the objective function. So this is what we're trying to minimize over the vector c and the set of vectors mu. And it's a sum over all of our data, so from I equals 1 to n, where for each data point, for each value of I, we sum over each of the clusters an indicator that the ith data point is assigned or not, whether it's assigned or not to the kth cluster. So this will be equal to 0 for k minus 1 values, and it's going to equal 1 for one value. And it's simply going to be an indicator saying, does ci equal k? And then that indicator is multiplied against the squared Euclidean distance of the ith data point to the kth cluster. So we calculate the distance of the ith data point to the kth cluster for all values of k. We square it, but then this indicator, through this sum, this indicator is only going to pick out the squared distance to the cluster that the ith point is actually assigned to. So it'll be 0 times a distance for k minus 1 clusters and 1 times the squared distance for the cluster that the ith point is actually assigned to. So another way to see this is by taking this objective function that we want to minimize over each ci and over each mu k, and writing it this way. For a particular assignment vector ci, we sum for each value k the total sum of squared distances of all of the data assigned to the kth cluster. So here we're summing over all values I such that the ith data point is assigned to the kth cluster, the squared distance of that ith data point to the kth cluster centroid. And then we sum this for the kth centroid, get this sum, and then sum it over all of the centroids. So this is the total sum of squared errors of the assignments. This is what we're trying to minimize. We're trying to find these centroids and find these assignments such that all of the data assigned to a cluster, to the same cluster, are close to the cluster centroid. And we don't care about the distance to any of the other centroids, only to the one that it's assigned to. So this objective is not a convex objective function. What this means is that we can say we want to find the optimal values for c and mu that minimize this, but we can't actually do it. We can only derive an algorithm to minimize this locally, meaning we can't take the derivative of this thing and find the perfect values for mu and c, but we can derive an algorithm that is going to continually improve this objective function and continually minimize it until it converges to a local minimum. Okay, so to minimize the k-means objective function, we need to have some sort of an iterative algorithm because we can't take the derivative with respect to mu and c and set both of them to 0 and solve. Also notice that our algorithm can't involve gradient methods because even though mu is a real valued vector, c is a discrete valued variable that we want to set and can take one of k values, and so it doesn't make sense to try to take the derivative with respect to c. So we're also not going to be able to derive a gradient method to minimize this thing, similar to how we did with, for example, logistic regression. So let's look at this coordinate descent algorithm. It's fairly straightforward. It's not more complex than what we've already discussed with gradient methods. We're going to discuss a specific example of coordinate descent for k-means. And so let's look at the k-means objective. Again, we want to minimize this thing over all the values of c1 to cn and over the vectors mu1 to mu k. And so instead of taking the gradient of this thing with respect to all the variables, which of course we can't because c is discrete, and instead of trying to somehow minimize it over everything at once, what we're going to do is we're going to split these model variables into two different sets. One set is going to be all the vectors mu, and the other set will be all of the indicators or the cluster assignments C. So we have these two sets that we're going to break our variables into, and they fall naturally into the two key variables in the model. And even though we can't find the minimum of this thing with respect to mu and C at the same time, we're going to see that if we, for example, held mu fixed, we could minimize this thing over C exactly. So for a particular setting of mu, we can find the best setting of C exactly. And also for a particular setting of C, we can find the best mu exactly. So if we hold C fixed, we can minimize this thing over mu very easily. And if we hold mu fixed, we can minimize this thing over C very easily. And so we're going to derive an algorithm that's like that, where we hold one fix, optimize over another set of variables, then holding that other set fixed, optimize over the first set, and iterate back and forth. So this is called coordinate descent. These are the two coordinates, and holding one coordinate fixed, we descend in the other coordinate. Okay, so here's the outline of coordinate descent. Again, it's very general, but I'm just going to present it now in the context of k-means. So we're going to input x1 to xn, where each x is in Rd. We're going to randomly initialize our centroids. That's one initialization. There are others that we could choose, but just imagine that we randomly initialize the cluster centroids. And then the coordinate descent algorithm for optimizing k-means iterates between these two following steps. First, in one iteration, we first hold mu fixed, and then for each value of Ci, we find the optimal value for each Ci. So we minimize the objective over each Ci separately given mu. Then the second step is to take those optimized Ci's, so hold C fixed, and now find the best vectors, mu k, for k equals 1 to cap k in Rd. That's going to minimize our objective for that particular setting of C. And then just keep iterating back and forth. So there's a circular way, if it's not obvious yet, why we need to iterate these two things. If you think about it, if we hold mu fixed, we're going to be able to say that we can find the best cluster assignments in the vector C that minimizes the objective function for that particular mu. But once we change C, we can probably find a better setting of mu for that new setting of C. So the mu is updated. The C is the best C for the first mu, the initial mu, but now that we've changed C, maybe there's a better mu that we can find. Similarly, if we find the best, most optimal setting for mu, given a particular setting for C, we've now changed mu, and so there's possibly a better C. So it's a circular way of thinking that every time we optimize a variable in the model, it's only optimal for the setting of the other variables. And then by optimizing it, those other variables perhaps now can be optimized even more. And the whole reason why we iterate back and forth is because mu and C, they depend on each other in the objective function. So they aren't separated from each other. The setting of C is going to impact mu, and the setting of mu will impact C. So when we change one, we're going to impact how good the other one is. Okay, let's look in more detail at the coordinate descent algorithm. Remember that the first step, we update C given mu. So we can call this the assignment step. It's where we take each data point in our data set and assign it to one of the capital K clusters. So for this step, we're given a setting for mu1 through mu k, and we want to update C1 through Cn. So the way that we update this is we look at our objective function. That's the thing that we're trying to minimize. And for this step, we're going to write it out in this way to make it a little bit more clear. So the way I've written this is I've expanded the sum over each data point to separate it. So here's the sum over each cluster assignment for the first data point through the sum over each cluster of the assignment for the nth data point. And we have one of these things in between here for every data point in between. Now our goal is to minimize this thing with respect to the vector c. We want to pick c1 through cn to minimize it. And so we need to come up with a way to do that. And if we look at this objective function, we see that whatever we set c1 to be equal to, it has no impact at all on what we set cn to be equal to. We can view these as n completely separate and independent problems given the setting for mu1 through mu k. So if we want to minimize c1, we want to minimize the objective over c1. We want to assign the first observation to one of the k clusters. All we need to do is focus in on this term here and minimize this thing independently of all of the other terms in the objective. So really, the optimization of, for example, ci is an independent optimization where we pick out the ith sum in this sequence, and we now minimize the sum of this. We minimize the squared distance from the ith data point to the kth centroid over the subscript k. So ci is simply going to be assigned to the cluster that has the minimum squared distance here. So in plain English, we're assigning xi to the centroid it's closest to. So notice that because ci is a discrete variable, can take one of k values, there are no derivatives here. However, because there are only k possible settings, we simply can calculate this distance and square it to each of the capital K centroids, and then pick the index of the smallest one. And so it's literally, for the ith data point, to assign it to a cluster, we literally are just searching all of the clusters and finding the one that the ith data point is closest to. Okay, so that's the assignment step. We've updated C, we've optimized the objective over C for a particular mu, because we have minimized each individual term over each data point, point-wise. Now we need to update mu. So we'll call this the update step. Given the assignments C1 through Cn, we want to update the cluster centroids mu1 through mu capital K. And so again, we're going to rewrite the exact same objective function in a new way. So this objective function is identical to the previous objective function, except we're now splitting the sum over k instead of over n. So now we sum over each data point in each individual term, and we do it for the first cluster up through the capital Kth cluster, and then sum each of those together. So we want to minimize this thing over all values of mu. And using exactly the same argument as before, notice that that updating this for mu1 is separate and independent from whatever the other values of mu are. Also important to remember is that ci can be only equal to one value between 1 and k. So for a particular value of ci, for a particular ci, this will be 0 for k minus 1 values, and it will be equal to 1 for only one of these, in only one of these terms corresponding to the cluster that the ith data point was assigned to in the previous slide. Okay, so we want to optimize this thing over mu k. What we do is we take the derivative of it with respect to mu k and set it to 0, and we find that we can analytically solve. And what we end up getting when we minimize this thing over mu k is that the update for the kth centroid simply sums all of the data that was assigned to the kth centroid and then divides by the number of data points in the kth centroid. So that's all this is saying. Take the average of all the data that was assigned to the kth centroid. In other words, we take the mean, you could think of it, of all of the data assigned to the kth centroid, hence the name k-means clustering. So here's the algorithm all on one slide. We're given data points x1 through xn. Each point is in Rd. Our goal is to minimize this objective function. This is the k-means objective function. And so what we do is we're first going to randomly initialize our centroids in some way, or initialize them in some way. And then we're going to iterate, updating c and mu until this objective function stops changing. So what we first do in one iteration, we update each ci by setting ci to be the index of the cluster that the point xi is closest to in the Euclidean sense. And then when we updated each of these cluster assignments, we update the cluster centroids by taking the average of all of the data assigned to a particular centroid. So for the kth centroid, we simply average all of the data that was assigned to the kth centroid according to the most recent update for the vector c. So let's look at a walkthrough of this. Here's our data set. Each of these points is a two-dimensional vector shown here. And now we want to cluster these data into two clusters, meaning we want to output for each data point an index of whether it was in the first cluster or the second cluster. And we also want to output the two centroids. So we want to output two vectors that are both two-dimensional, where each vector is the center of its respective cluster. So just to make it clear, let's assign the first cluster centroid to be here and the second centroid to be here. Now if we run k-means, we're in the first iteration now. The first step within the first iteration is to assign all of the data to the nearest centroid. So all of the data to the right side of this pink line is closest to this centroid, and so all of these data points are going to be assigned to the red cluster, so they're colored red, and all of the data to the left of this pink line is closest to this centroid, so they're all going to be colored as a blue cluster point. The next step is now to take all of these red data points and average them and update the centroid for the red cluster, and we get this update. The average of all of these red points, because there are many more points, it's more dense in this region, the average is going to be right here. And similarly with the blue points, we average all of their values. There are many more points in this region, which is much more dense, and so these points drag the centroid, drag the average to right here. So that's one iteration of k-means. And now we just keep repeating this. So we have the new centroids. We again assign each data point to its closest cluster, indicated by the color. And then we update the centroids by averaging all of the data that was assigned to that cluster. So we average all of the red points to get an update of the red centroid, and average all of the blue points to get an update of the blue centroid. And we keep repeating this by assigning and then averaging. And eventually we stop. The algorithm's now converged. These are our two clusters. And what we return are these 2 points. These are the two centroids, say mu1 and mu2. And we also return for each data point an indicator of which cluster it belonged to. So all of these red points, if this is the ith data point, then ci will be 1 for this data point. And if this is the jth data point, then cj will be equal to 2 for that data point. So we have those two things that are returned. Now if we looked at the objective function of k-means, if we actually plotted this function L, what we'll see is something that looks like this. So we have the update of c here. The blue dots are after updating c. The red dots are after updating mu. So after each red dot, we've completed one iteration. So here's 1, 2, 3, and 4 iterations. And we get something that looks like this. Now in practice, if we have a lot of data, maybe it'll take many iterations to converge. What we could also do is simply monitor this thing and then stop when it stops changing very much.